Okay, friends, welcome back. Now, let us see how this can be implemented. So, for implementing this, let us write the truth table for this. So, we have two inputs J and K, and we have one more input which is the feedback input. So, at nth stage, at nth instant, we have some Jn, we have some Kn, and we have Qn, that is a current output. And taking these three into consideration, the next output will be created, which we call Qn plus 1. Okay, now just I have made this four parts considering the JK combinations. So in these two, JK combinations are 0 0. Here it is 0 1. Here it is 1 0. Here it is 1 1. And according to this, it says if it is 0 0, there is no change. So Qn plus 1 is same as Qn. So this was 0 here. Now it will be 0. This was 1 here. Now it will be 1. For 0 1, the output is going to be reset action, so that is 0. It doesn't make any difference what was earlier, therefore in both cases it is going to be a 0. For 1 0, the output is going to be 1 independent of what was earlier, therefore both cases it is 1. For 1 1, it is toggle action, that means whatever was previous, its opposite will be the 1. So here it was 0, now it will be 1. Here it was 1, now it will be 0. So that's the output possible for Qn plus 1. So just put that. So 0, 1, 0, 0, and 1, 1, 1, 0. So that's what is the K map for Qn plus 1. So you can see there are three pairs possible. So this pair says Jn and Kn bar. That is this pair. This pair says Kn, Qn. I'm sorry, this is Kn bar, Qn, and this one says Jn and Qn bar. So Jn, Kn bar is this combination, and this combination is Kn bar, Qn, and this combination, this one and this one, we say Jn, and here it is Qn bar. So if you just take the, so this is J, this is K, this is Q. So we need JK bar, then we need K bar, Qn, and then we need J and Qn bar. All three are odd. This is what is Qn plus 1. Done. So what should we do with this? This is just a, so I think this Qn and this Qn plus 1 have something in common. So what can we do? Yes, if we can connect a D flip flop here, if we can connect a D flip flop here, then whatever was there at nth instant, that was stored in this D flip flop and is now available. And when the next clock is given, so the current J value, current K value, current the past Q value, all are going to decide what should be next Q. So this is internally connected, and this whole thing, if you just look from outside, then we have something like this, and that's what is a JK flip flop. So that's what is the JK flip flop. So J input here, K input here, clock is here, and internally this is fed back. So which is all this circuitry is inside this block. So we don't need to represent this each time. So just we represent it with one block and say this is JK flip flop. And property of this is it works according to this. So when JK both are 0, the output is going to be same as it was earlier, so there won't be any changes possible. If J is 0, K is 1, irrespective of past, the output is going to be 0, this is going to be 1. And if it is 1 0, J is 1, K is 1, irrespective of the past, this is going to be 1, this is going to be 0. And when this is 1 1, J is 1, K is 1. Then if it was 0 earlier, it is going to be 1. And if it was 1, it is going to be 0. And that's what is going to happen. You find any problem in this? Yes, I do find a problem in this. And that problem is, say, if the clock is represented by this, the clock is high for some period, then in that period this is going to get activated. And if it is 0 0, no change, not a problem. If it is 0 1, it becomes reset, whatever be the length of it, not a problem. If it is 1 0, it sets, whatever be the length, it is going to remain same. So these three conditions we are not going to face any problem. But yes, we do find a new problem with this. So that's life, friends. Buy one get one free. When you try to solve one problem, yes, we had a second problem ready for us. What is that problem? So let's assume that this feedback effect takes some time t, and we are giving the clock for some period tc, and the problem is when t is smaller or very much smaller than tc, then what would happen? So that the output assume that output was 0 when we started, and the inputs j and k are 1. J is 1, k is 1. So what would happen? So clock becomes 1 at this point, and when clock becomes 1, it says what are the j values, k values. J, k both are 1, and what is current output? Output is 0, therefore output becomes 1. And in a period, it needs some period t to become 1. And once it becomes 1, clock is still high, and it says clock is high. What is jk? 1 1. Then what is current output, it is 1. Therefore, this is 1 1 1 1 1 1. Output should become 0. So output has become 0. Then this takes another t time. Then in that, after that t time, its clock is still high, j is 1, k is 1 still, and then it looks what is q. Q is 0. Therefore 1 1 0, output should become 1. So it becomes 1, and then becomes 0, then becomes 1, then becomes 0, then becomes 1. So as long as the clock is high, this continues, and this is called a race around problem. This is called a race around problem, racing problem. Because of this loop, there is sudden continuous on off action, and this has a big problem in our digital circuitry, because we expected that it's going to do only once, but it has done multiple times and switched between on and off multiple times, and the final result depends on what was the last action taken. So it may be going on or it may be going off. So it is uncertain, because the T and TC are independent of each other, and hence you can't just predict what could be the last action happens. That is one problem. Second thing is, in between, you see a lot of noise created, and which is not advisable. So this has to be somehow solved. So how this is solved, that's what we need to look in our next session. So till then, take care, see you, bye.